This lesson is about the derivatives of algebraic functions. At the end of this lesson, you must be able to identify the different differentiation rules that we can use to differentiate algebraic function and to make use of these rules properly to determine the derivative of algebraic functions. Today, we will look at some differentiation formulas. These are formulas that are obtained by applying the definition of the derivative to some commonly encountered functions. The first of these differentiation formula is on the derivative of a constant. The theorem states that the derivative of a constant function is 0. That is, if c is any real number, then the derivative of c with respect to x is 0. Another most commonly encountered function is the power function, where y is defined equal to x to the n. The theorem to differentiate a power is stated this way. If n is a positive integer, then the derivative of x to the n with respect to x is given by n times x to the n minus 1. In words, to differentiate a power, what we do is we decrease the exponent by 1 and then multiply the resulting power function by the original exponent n. Though this rule states that n is a positive integer, this can be applied to any n, a real number. In differentiating a constant times a function, if f is a differentiable function at x and c is any real number, then the product c times f is also differentiable at x, and that the derivative of the product c times f of x is given by the product of c times the derivative of f of x. That is, if we are multiplying a constant times a function, then its derivative is equal to the constant times the derivative of the function, if this derivative exists. In differentiating a sum or a difference of functions, if f and g are both differentiable functions at x, then their sum f plus g or their difference f minus g are likewise differentiable, and that the derivative with respect to x of the sum or the difference of the functions f and g would equal the sum or the difference of the derivative of f with respect to x and with the derivative of g with respect to x. That is, the derivative of a sum or a difference of functions would equal the sum or the difference of their derivatives. When we have a product of function, say f times g, if f and g are both differentiable functions of x, then the derivative of the product f times g with respect to x likewise is differentiable with a derivative equal to the sum of the product of one function with the derivative of the other. Hence, we have f times the derivative of g with respect to x plus g times the derivative of f with respect to x. Dealing with the ratio of two differentiable functions, f divided by g, then the derivative of the quotient of f to g is given by this rule. That is, the derivative of f divided by g with respect to x would equal a ratio of the difference defined by g times the derivative of f with respect to x minus f times the derivative of g with respect to x all over the square of g. Now please take note that always you start with the denominator g times the derivative of the numerator minus the numerator f times the derivative of the denominator g to be divided by the square of the denominator. Okay, let us now apply the differentiation rules differentiating on the given functions. For number 1, we have y is equal to negative 5. The form of the function is just a constant function, hence the derivative y prime is equal to 0. Given y equal to x to the 6, the function is a power function of the form x to the n. Differentiating x to the n, the derivative would just be given by n times x to the n minus 1. Applying that here with n equal to 6, the derivative y prime would be given by 6 times x to the 6 minus 1, or we have y prime equal to 6 times x to the 5th power. The third example defines y product of 8 with a variable function x to the negative 7. The derivative of this given function would be given by the product of the constant 8 with the derivative of x to the negative 7. Now, x to the negative 7 is fitted to the form x to the n. Remember, we mentioned earlier that n can be any real number. Hence, the derivative y prime would just be given by the product of the constant coefficient 8 times the exponent negative 7 times x to the negative 7 minus 1. Or we have this equal to negative 56 times x to the negative 8, which we can write in terms of y prime is equal to negative 56 divided by x to the 8. Number 4 function is a polynomial function where we have a sum of a number of terms. Y defined in terms of 9x to the 8 minus 7x to the 6 plus 5x to the 4th. In differentiating y, we will be applying the rule differentiating a sum or the difference of functions. Hence, the derivative is obtained by adding up the derivative of 9x to the 8, the derivative of negative 7x to the 6, and the derivative of 5x to the 4th. And these derivatives are as follows. For 9x to the 8, we have the coefficient 9 times the exponent 8 times x to the 8 minus 1. The second term would be given by product of negative 7 with the exponent 6 times x to the 6 minus 1, and the last term given by 5 times 4 times x to the 4 minus 1. Simplifying this to the form 72x to the 7 minus 42x to the 5th power plus 20x cubed, or if you want to factor out the common factor among the constant coefficients, then y prime can be expressed equal to the product of 2 with 36x to the 7 minus 21x to the 5th power plus 10x cubed. For our 5th example, we have here y defined product of x cubed minus 1 with 5 minus 2x. In differentiating this function, since we have here a product, then we will be applying the rule to differentiate a product, wherein y prime is given by the sum of the following. The first function, x cubed minus 1, times the derivative of the second factor, 5 minus 2x, which is just a negative 2, plus the other factor, 5 minus 2x, times the derivative of x cubed minus 1, giving us a 3x squared. When we multiply on these factors as indicated, then we will have y prime equal to negative 2x cubed plus 2 plus 15x squared minus 6x cubed. And when we simplify this by combining similar terms together, that is combining the x cubed terms together, then y prime will just be equal to negative 8x cubed plus 15x squared plus 2. In number 6, the function y is defined as a quotient or as a ratio of functions 3x squared minus 1 to 2x plus 3. So when we differentiate this function, we will be applying the rule to differentiate a quotient where we have the derivative equal to the denominator 2x plus 3 times the derivative of the numerator 3x squared minus 1, which will just give us 6x, minus the product of the numerator 3x squared minus 1 times the derivative of the denominator, which is a 2, to be divided by the square of the denominator 2x plus 3. When we multiply the factors given in these terms and we combine similar terms together, y prime would be given by 12x squared plus 18x minus 6x squared plus 2 divided by the square of 2x plus 3, or we will have y prime equal to 6x squared minus 18x plus 2 divided by the square of 2x plus 3. Or finally, write this as equal to 2 times 3x squared plus 9x plus 1 divided by the square of 2x plus 3. To summarize what we have just had in this lesson, in differentiating a function, we did not go through the 4 steps suggested by the definition of a derivative of a function. Rather, we can just apply appropriate differentiation rules to differentiate commonly encountered algebraic functions.